Hey everybody, Dr. A here, and in this video we're going to be discussing permanent deformation. Okay, so let's go ahead and get started and provide us some background information on what this means. So when a material is loaded beyond its yield point, it will sustain permanent deformation. Now, even if that load is removed, there will be permanent strain, okay? So what does that mean? Well, let's draw a diagram together. So let's say that we have a material that has a stress-strain diagram that looks something like this, okay? Now, we have that initial linear region, and then we get to kind of this nonlinear region where we have the onset of yielding, or yielding is nearly occurring, and then we have an increase in stress, and then we have a decrease in stress, and then we finally have failure here, okay? So what are we referring to when we talk about permanent deformation? Well, what we're referring to is when we go beyond this little region. Now, in this diagram, this part of the graph is exaggerated. This is a very small part of the graph in reality. When we go beyond this little initial nonlinear region, that's when we're going to have permanent deformation. And so even if you take the load off, you're going to have a permanent deformation, okay? And that's before it ever actually fails, all right? So the question becomes, how do we quantify or compute this permanent strain or permanent deformation? Okay, so let's make a note of this here. What we do is we're going to say to compute the permanent strain, which I'm going to call that epsilon perm, we use a graphical procedure where we draw a line from the load point back to the epsilon axis, following a path parallel to the linear portion of the diagram. Okay, so what does that mean? Okay, so let's say we have this stress-strain diagram. Let's say that this is a material and we're putting it in a tension test, for example. So we start increasing the load. Now we start increasing the load, and what happens as the stress is increasing? As stress is increasing, your strain is also increasing. So you're increasing, you're still linear elastic. What happens if we cut the tension test machine off right here? Well, what will happen is that specimen will rebound back to its original form, which would be back to zero. So as long as your loading is below that proportional limit, you are going to be within this linear elastic region. And so if you remove the load or you turn off the tension test machine, what will happen is your stress will go back down, and so will your strain, and everything will go back to zero. No permanent deformation, okay? But let's say you keep loading, you get past this proportional limit, and you start going into the non-linear region here, okay? Let me draw that a little bit better. We go forward and we go to the non-linear region, okay? So now we have exceeded the proportional limit and yielding has begun, okay? So the question becomes, if I cut off the tension test machine, or if I remove the applied load, what will that specimen do? Will it actually rebound back all the way to 0? And the answer is no, okay? What it will do is, let's say you've loaded it up to this point right here, okay? Up to this point. What it will do is you will recover some of that deformation, okay? But you will not recover all of it. What will happen is there will be some permanent strain left in that specimen, okay? And so how do we quantify that? We use this graphical procedure. And what we do is we draw a line from the load point back to the epsilon axis, following a path parallel to the linear portion of the diagram. So let's say we load this sucker. We load it to right here, okay? So it's loaded to this stress value, whatever it is, okay? Sigma. And then we cut the load off. We remove the load. So what's going to happen is your specimen will follow a path back to the strain axis, and that path will be parallel to the original linear portion of the stress strain diagram, okay? So this green line, the path that it follows back to the epsilon axis, these are like little arrowheads, this line is parallel to this line. Now, if those two lines are parallel, what are their slopes? Well, the slope would be E for both of them, right? Parallel lines have the same slope. So that has a slope of E, but notice that it is displaced over, okay? You're never going to go back to the origin in this case, all right? So then the question becomes, what is this permanent deformation? Well, the permanent deformation or the permanent strain is this value right here. This is epsilon perm. So the permanent strain is that distance. It's the distance from the origin to where the rebound curve intercepted the epsilon axis, okay? So what we sometimes call this is plastic strain, or we say that the material is subject to permanent set. So we'll write this sentence. Epsilon perm is sometimes called the plastic strain, and the material is subject to what's called permanent set. Okay? Now, here's another question for you. How much has this material rebounded? What is the amount of strain that is recovered? Okay? So the answer to that comes from taking that point of loading, and we drop a vertical line down to the epsilon axis, and we have this point right here in blue, okay? So this distance, the distance between the green point and the blue point, this is going to be called epsilon recovered, okay? Which I'll label epsilon rec. Okay, so maybe let me relabel these a little bit better so it's a little bit more organized. So the distance between the green and the blue point is epsilon recovered, and then the distance from the origin to that green point on my figure is epsilon permanent. Okay, so epsilon recovered, this distance right here, represents the amount of strain that has rebounded, that you have recovered. So it's like how much the specimen bounced back, okay? So it never goes back to its original shape, but you're gonna rebound some of that deformation, okay? And then the permanent deformation is right here, okay? And so now what happens is that material, or that specimen in particular, has now had an alteration of its material properties. So now it would always follow this new path, okay? So moving forward, its material properties would follow this modified path of the stress-strain relationship. Okay, so hopefully you found this video helpful and it improved your understanding of permanent deformation. If this video was helpful to you, please hit like and subscribe, and be on the lookout for other videos like this, including a numerical example where we explore this concept again. Thanks for watching.